Fourier's law is an important component of the general theory we seek of the energetics of thermoregulation. It applies mostly to endothermic homeotherms, the birds and mammals. This general theory helps us understand several aspects of the selective advantages that accrue to animals that adopt a high metabolic energy lifestyle. This general model is the work of one of the greatest comparative physiologists of the 20th century, Per Scholander. Scholander made major contributions to the physiology of humans and other animals living in extreme environments. He also made significant contributions to the physiological adaptations of plants. One of his major contributions was working out the theory of the energetics of thermoregulation in homeotherms. His model is called the Scholander model. Let's start, as we did before, with a body in energy balance with its environment. We can write a simple energy balance for this body, which is the heat in, Q dot sub in, and the heat out, Q dot sub out, that must add up to zero. It doesn't matter what the respective temperatures of the body and environment are, but if the body is regulated at a constant temperature, these two fluxes of heat must always add up to zero. This is the basis of Fourier's law. Now, let's break down these fluxes of heat in a bit more detail. We've already mentioned the importance of metabolic heat production, which is always a heat input to the body, which we will symbolize with the letter M. We're keeping our sign convention from the previous example, namely saying that all fluxes of heat into the body have a positive sign. All animals are wet, and if they happen to live in air, they will always be evaporating water from their wet surfaces. There's a heat flux that goes along with this, and this heat flux is always going to be negative. That is, evaporation will always cause a net loss of heat from the body. According to our sign convention, this will always be a negative heat flux, and we'll symbolize that flux with a letter E. As an aside, you may be thinking that this can't be, that if water condenses on the body, there will be a net heat flux in. That's why steam burns. The condensation of hot water vapor actually transfers heat into the body. I'm going to tell you a little bit later why, for living animals, it's impossible for this evaporation term to ever be anything but a negative value. There are also various ways that heat can be transferred physically between the body and environment. For example, if the animal is in contact with some kind of substrate that differs in temperature from its body, there will be a heat flux by conduction. This heat flux can go either way, either into or out of the body, depending upon whether the substrate is warmer or cooler than the body. We'll symbolize that heat flux with a letter K. If the animal is living in a fluid environment that differs in temperature from its body, there may also be a transfer of heat by the process of convection. We'll symbolize this with the letter C. Like conduction heat flux, convection heat flux can be either positive or negative, depending upon whether the fluid is warmer or cooler than the body. Finally, there may be a flux of heat by radiation between the body and environment. We'll symbolize this with the letter R. Like these other heat fluxes, radiation heat flux can be either positive or negative. An animal basking in the sun will experience a net radiation heat input, for example, and an animal under the cold night sky will experience a negative radiative heat flux from its body. We can take all these terms and write an energy balance equation just as we did for the simple one we wrote above. We'll write them in this order, which makes for a simple acronym, MERCK. Again, if the body temperature is being held steady, as it would be in an endothermic homeotherm, all these terms must add up to zero. Okay, let's rearrange this equation a little bit. We'll isolate metabolism and evaporation on one side, and radiation, convection, and conduction on the other, and we'll get an equation that looks like this. Now, this is important because it has enabled us to isolate the so-called physiological heat fluxes on one side of the equation, namely metabolism and evaporation, and the so-called physical heat fluxes on the other. This energy balance equation is the foundation of the Scholander model. Before we get to the actual Scholander model, though, we have one more term to define. Metabolism and evaporation together can be combined into one term, which we'll symbolize with the letter N, which is the net metabolic heat production. Unlike metabolism and evaporation, which must be either positive or negative respectively, the net metabolic heat production can be either positive, negative, or zero, depending upon how metabolic heat production and evaporation heat loss add up. Keep this in mind as we develop the full Scholander model. Let's now take this equation and recast it in terms of the Fouriers Law analysis we did earlier. Now we plot heat flux, Q dot, versus the difference between environmental and body temperature. Remember that the left half of this axis is the condition where body temperature is warmer than environmental temperature, and the right part of the axis is where environmental temperature is cooler than the body temperature. If we plot the magnitude of the physical heat fluxes, namely the sum of the radiation, convection, and conduction heat fluxes, we'll get a curve that looks like this, namely a straight line with a slope equal to the total thermal conductance, K sub T. In the upper right quadrant, where the environment is warmer than the body, heat fluxes are positive, that is, they are directed into the body. In the lower left quadrant, where body temperatures are warmer than the environment, heat fluxes are negative, that is, they're leaving the body. Because of conservation of energy and the energy budget equation that we just outlined, we can plot the net metabolic heat production, that is the sum of M plus E, and this will also be a straight line with a slope equal to the negative of the thermal conductance. The Scholander model itself is derived from this analysis. It's also derived from the need to explain certain patterns of metabolism of homeotherms with respect to environmental temperature. We'll start with a plot of metabolic rate versus environmental temperature. The original empirical observations expressed metabolism as a rate of oxygen consumption, but as we know, this is fundamentally a metabolic rate, that is an energy flux rate, and so we'll make our plot in terms of the metabolic heat production. The empirical patterns of metabolic rate that have been observed look something like this. There's a linear decline of metabolic rate with increasing environmental temperatures, down to a baseline metabolism known as the basal metabolic rate, or the BMR. There, the metabolic rate stays up to a certain environmental temperature where it doglegs up into another linear increase of metabolism. There are a few other geographic points on this curve that need to be defined. The first is the temperature of the lower dogleg in the metabolism curve, where the linear decline of metabolic rate with increasing environmental temperature levels off at the basal metabolic rate. The temperature at this dogleg is known as the lower critical temperature, or T sub Lc. From the lower critical temperature, even though metabolism stays level at the basal metabolic rate, the curve extrapolates to a point on the x-axis where the environmental temperature equals the body temperature. When body temperature is regulated, this is a fixed point. Finally, the upper dogleg, where metabolic heat production begins to move sharply upward, is known as the upper critical temperature, or T sub UC. Finally, the slope of the metabolism curve at environmental temperatures below the lower critical temperature is equal to the negative of the animal's thermal conductance. Scholander's explanation for this curve derives from the energy balance analysis that we've just completed. The metabolism at environmental temperatures below the lower critical temperature is a straightforward derivation from Fourier's law. This is why we can confidently claim that the slope of this portion of the curve is going to be equal to the negative of the thermal conductance. The dogleg portion of the curve at environmental temperatures above the lower critical temperature reflects the fact that metabolism of animals cannot fall to zero. If it does fall to zero, that's a dead animal. So there has to be some basal level at which metabolism sits and cannot fall below. The fact that the curve extrapolates to an environmental temperature equal to the body temperature is also a straightforward derivation from Fourier's law. It's only at that point that the net metabolic heat production can equal zero, and we'll come back to this point later. The upper critical temperature and the sharply increased metabolism at temperatures above that is also straightforwardly derived from Fourier's law, but there are some other implications to it. For example, the curve of metabolism, like the metabolism curve at temperatures lower than the lower critical temperature, must extrapolate to an environmental temperature that is equal to the animal's body temperature. Aside from this sharply increasing metabolic rate usually derives from the metabolic costs of increasing the evaporative heat loss from the animal at high temperatures. It takes energy to generate sweat, for example, and it takes energy to do things like pant, or move around, or change posture, things that enhance the cooling of the body. And again, we'll come back to this problem later. The plot of metabolism versus environmental temperature is only one aspect of the Scholander model, but it's the one that's most often presented. We're going to be focusing quite a lot on this part of the Scholander model, but there is an additional part to it, namely the role of evaporation. Let's start with our plot of metabolism versus environmental temperature, with all the landmarks and whatnot indicated on them. Remember, however, that metabolism is only one part of the so-called net metabolic heat production. Evaporation is the other. So, to be complete, we need an additional plot of the environmental heat losses versus environmental temperature, namely from evaporation. If we plot out what evaporation should look like, it will follow a curve that looks something like this. The explanation for this pattern also relies on the Fourier's law analysis we described earlier. The evaporation heat loss ticks along at a more or less steady rate at about minus the basal metabolic rate for heat production. At the lower critical temperature, there is a significant dogleg, and the evaporation heat loss increases, which, because it's negative, will have this downward slope. The slope of this portion of the evaporation curve is in fact identical to the slope of the metabolism curve at temperatures lower than the critical temperature. That is to say, the slope here is also minus K sub T. This makes sense in terms of the energy balance that drives this whole thing. The energy budget must always be equal to zero. That is, the net metabolism must always equal the physical fluxes of heat. Just because metabolic heat production can't fall below the basal metabolic rate, it's heat production nevertheless. And as environmental temperatures increase beyond the lower critical temperature, this will have implications for the physical losses of heat. The whole thing is brought into balance by an increased evaporation heat loss. The same applies to the pattern at temperatures above the upper critical temperature. Let's say this has a slope of minus K sub E. As environmental temperature increases and body temperature is held at the same value, the physical influxes of heat will increase. Just because the animal is incurring additional metabolic costs to maintain its body temperature does not excuse it from the first law of thermodynamics. The energy budget has to be balanced somehow. And it's balanced by having evaporation heat loss that not only accounts for the physical changes of heat, but accounts for the increased metabolic heat burden as well. The slope of this curve will be the sum of the thermal conductances both below and above the lower critical temperatures. This completes our derivation of the full Scholander model. It's a remarkable melding of physics and physiology, taking an empirical observation of how metabolic rate changes with environmental temperature, and uses a simple physical analysis to explain it and to make predictions about how the heat budget can be balanced.